everybody. I hope everyone's having a wonderful day. So last day I started talking about how the rotate operation works. So remember, this is going to be the simple operation that we're going to use when we talk about our rotations for how we're going to correct the tree whenever it becomes imbalanced. So remember, the big idea here is that we're going to rebalance the tree from the smallest subtree that becomes imbalanced at that time. What does it mean to be imbalanced? Remember, an AVL tree must maintain the height balance property. So the height balance property, remember, is that its children, the tree's rooted at its children of a given node, its heights cannot differ by more than 1, right? So to do this, the trains are excited. The train people. What we'll do is we'll use this rotate operation. We have right rotates and left rotates. So the idea in a right rotate is you imagine I take x and I promote it up to become the root of the subtree, and I demote y. Now, I want to give a couple of tips about this, is that I need to make sure I maintain the heights of the nodes. Now, in the notes I mentioned about this later, but I may recommend mentioning this here, because our operations are comprised of these, is that whenever I update these, notice that these are still subtrees, right? Now, when I move this subtree around, does its height change? No, right? However, so x and y's might change, however. Why? Because remember, these are just subtrees, right? They're just children of x and y at some point. So how would I update the height appropriately here? So notice that y, when it gets demoted, it becomes the root of the subtree that is of T2 and T3. So does that mean I need to update the height of y? Probably a good idea, right? So I would want to make sure I update the height of y before I update the height of x, because x, remember, x's height is now, it might be different, right? So we need to make sure we update that. So all I'm saying is you make sure you need to update the heights of the nodes when you do this operation. The order does matter. If I, for example, update x's height before y's height, and y's height changes because now it has this new subtree here. Because remember, before it had this one right here already. I already had T3 here already. But T2 might look a little different. Okay, so that's why we have to make sure we take into consideration the order in which we compute the heights. The other one, more practical, and I promise if you're implementing an AVL tree, this will be the thing that causes all your hair to fall out. It's this one right here. As you can see, that happened to me several years ago. The point is that make sure you don't forget the parent-child references. Because remember, in my picture here, I don't show the parent and the child, I just show an edge, right? There's still a parent reference and a left and a right and a parent. And there's also a parent technically up here too. So you got to make sure if you modify what the child is of the node above this one, if this isn't the root, you have to make sure you update its child, right? So this is a very important implementation specific detail I want to make sure you know, because that does creep into how you do your debugging if ever you were to implement this thing. And it'll cause you an absolute nightmare when you're debugging if you don't take this into account. So that being said, let's talk about these 4 rotations that I talked about. So these are going to be the 4 rotations that your AVL tree is going to do whenever an imbalance occurs. So remember, we're going to imagine this that we're going bottom up. So from wherever I put or remove, I'm going to work my way up the binary search tree to where the height balance property gets invalidated. So I want to imagine that node being Z. So there's really 4 possibilities that could really occur. That's my big claim. I'm not going to prove it for you, but there really just are 4. It should be very natural to see this once you see all the rotations. So what happens is I have the height differing by more than 1 between the left subtree and the right subtree. But it occurs really somewhere going on this right subtree. So do you see really where the problem lies here? in the RR rotation. So in our this is where we're going to do our RR rotation. What we're going to do is, how am I going to fix this? Now remember, you got to imagine this like the floor is lava, okay? So we don't want T2 to touch the lava. What do we need to do? We need to make sure we bring T2 up. Where should be the best way to pivot using my... So remember the hanger? Remember, we're going to imagine I want to take... Where should I put the hanger to pull this up to try to balance it by pulling off some weight and lopsiding it a little bit better? Where should I put it? Should I put it here? Should I put it there? Or should I put it here? Maybe where I have the Y there, maybe that dark spot there might be the good spot. Now imagine if I were to rotate, so I pull Y up to where Z is, and I pull down Z. So I go like this. Should that help? It seems to. It seems to be quite natural, right? I'll get into more detail why it's called an RR rotation, but what you're going to do is you're going to apply rotate on Y, which what it'll do is it will promote Y to become the root of this subtree, and its left child is now Z, and the right subtree's root is X, okay? So all I've done is I've just went like this, like that. And then I've just moved T2 over to be belonging, well, T2 stays here, T1 is the one I'm talking about. So notice T1 now has been moved over to Z. Gotta imagine like I'm pushing that weight onto the other side so it stays level. Now notice that, look, now we're doing a little bit better, right? Notice that the height changed of the overall tree that I have here, right? So notice now we're going to satisfy the height balance property, at least of this subtree. So this subtree rooted at Y is now AVL. We might have to work our way up the tree to potentially make any other corrections appropriately depending on what operation we're looking at. So in a single rotation, what you're going to do here is you're just going to apply rotate on Y. So just rotate on Y will promote that and it'll form the correction that you need. So fortunately, single rotations are, because of this, I only apply rotate once. That's why it's called a single rotation. Likewise, the symmetric case is the LL rotation that we might need. So it looks like this. So Z is where the imbalance occurs, and it just happens to be on the left now. I apply now the LL rotation. I pull this up because I want to get T1 away from the lava, okay? And this correction will now make it so that it's going to remedy up that mistake, which is quite nice, right? So it's fixed for this tree rooted at Y. So what am I doing here? Again, I'm just applying rotate to Y. Remember, that's why we call it a single rotation. So the tallest child of Z is the one I'm going to perform rotate on. So depending on which of these two, I apply the rotate. And that's in the case of a single rotation. We have to be very careful because there's also the other two, which I'm going to illustrate by showing you one of them. It's called a double rotation. So our last two are the double rotations. And now, it's going to hopefully become apparent how you identify these four different rotations. So notice that in this case, I always identify it by, whenever I check my taller of my two children, what happens is I pick that one and then I look at the taller of those two, and then I look and see where the tallest one is. If it's on my left and then on the left again, that's where the name of it comes from, right? Left, then left is LL. Right, then right is RR. In a double rotation, what happens is you form a zigzag or zag-zig pattern. So what do I mean by this? An RL rotation would be where the tallest of the two children is going to end up being Y, and then the tallest of Y's children is X. But X is on either the left or the right, depending on if this was on the left, and then that would be on the right or right on the left. It forms a zigzag pattern. Or if it were the other way around, it would be a zag-zig pattern. So what do you do here? And this is why we call it a double rotation, is as follows. How do I correct this? Well, this looks a little bit different than the other scenarios. The structure is a little bit more complicated looking. So I'll ask you a very basic question. Okay, how would I fix this tree? How would I fix that one? Assuming that it was the problem case. Well, we know that this is really lopsided, right? So what would you do if this is lopsided like this? So I know the overall tree is imbalanced, but this one may not, this one isn't, right? This is the smallest subtree for which the imbalance occurs. How can I pull this up and push potentially that down? I use a rotate operation. Where should I do it? I want to pull X up, right? So what is that? I need to apply rotate on X. I apply rotate to X. What will happen is this will pull X up and push Y down, and then a trade-off will occur. And then what happens? What else do I need to do? So now remember, I don't necessarily have a guarantee that I've corrected the pattern yet. So what can I do now, seeing as it looks like something I've already done before? Once Y is down here, what does it look like? I'll give you a hint. It looks kind of like this, isn't it? So instead it'll be ZXY. How did I fix there? How did I fix that? I use an RR rotation. But where is X now? X is right here. So it looks like this, right? And so it's Z, Y, and X X, then Y. So we've got Z, X, then Y. So I have R, and then the R looks like this. How do I know how to fix that? I use an RR rotation. But what's an RR rotation now? That is just rotate on whatever I had in black, which is X, right? So in a double rotation, you apply rotate twice on X. So normally when we have a rotate operation, we assume we get back the root of that subtree. So that's why we call it a double rotation. It's because you perform two rotate operations. Is that clear, everybody? So that's what the RL rotation does. Naturally, you can see how you can do the LR rotation. It's just symmetric with this, and the same idea applies. You just use rotate X twice. Does everybody see that? That's all you're going to do. I'm not going to prove it here, but using these rotations will fix it. And hopefully the pictures will help see that. So notice the gap, it goes away as soon as you apply these operations. Just for the sake of time, I'm not going to prove that for you. So, what are we going to do? Before I get to anything too crazy, two things. How do you determine which case to apply? How do you determine that? You can determine if the imbalance node is encountered if you just check the height balance property, right? You just check the height of the left subtree and the height of the right subtree, which is just the height of the nodes of its children. If it falls out of line, then what do? You determine which of the two is the tallest. The tallest being the one with the larger height. So if it has the larger height, then what you're going to do is you're going to check its child. And you're going to say, hey, look, which of my two children is the taller one? So how do you determine which case to use? It's determined by the pattern for which you go through the determined Z, Y, and X. Actually, this one should be like this. Z, Y, and X. So The direction for which you travel tells you which rotation to apply. And the fortunate thing is if you implement rotate correctly, you should be able to do these these two, the zigzag and the zag-zig will be analogous to just applying rotate X twice. And here's just rotate Y. As long as you can identify between the single rotation, the double rotations and the single rotations, you're all hunky-dory. It's good stuff. How long do these rotations take? How long does rotate take? How long does rotate take? Each one of these is just reassigning the parent, the child, and potentially any other references that are involved in the rotate operation, right? So each of these rotates takes big old one time to perform. I have to update the heights of the nodes correctly, and I just have to update parent-child references. Each of those modifications takes constant time. So these are a constant number of manipulations. So for example, if you really don't like these rotate idea, you could literally go to each one of these and hard code in what the rotate looks like, the rotation is. If you want to if you quite literally just want to detect each of the four, and you could just literally just hard code this if you wanted to. I find this very natural because it makes the actual writing of the rotations a little easier. So any one of these rotates takes big old one, so it takes constant time. So how long does any one of these rotations take? So each rotation, so when I mean that, I mean the RR rotation, the LL rotation, the RL rotation, the LR rotation, takes constant time. So that's a really nice feature of this tree if we maintain the heights. So now we have a mechanism to perform the corrections on the smallest imbalanced subtree. So what are we going to do now? What are we going to do? All we need to do is work our way up from wherever we made a modification in the tree, correct any imbalance using these rotations, and as we work up the tree, we're going to make sure we update the height. Does the game plan make sense to everybody? So that's all we're going to need to do. It's really not that bad at all. So at first this looks really complicated, but the biggest part you'll find is just dealing with a little bit of the surgery, but the concept hopefully should make sense. This stuff isn't too terribly bad. Just don't let the complicated nature of having four rotations look weird. Remember, a single rotation just is applying rotate on Y, and a double rotation is applying rotate on X. And whatever rotate returns, it'll just be the root of that subtree that you perform the correction on. Okay, so let's talk about, remember, I told you that there's really only two operations we have to look at, right? Just whenever we do a put operation and when we do a remove. Now, I'm not going to rewrite what put and remove are, I'm just going to reuse them in a clever way. So I might make a couple small tweaks to how they work, but they're really trivial things to do. So let's talk about putAVL first. So what we're going to do, so we're just going to first apply put. So remember, put will put, it's a little strange saying, put will insert the node, a new record into our binary search tree. And obviously, it'll tell us if it done it correctly or not. I'm just going to assume there's no duplicate keys when I do this. So I'm just going to do this put, and then I'm just going to rebalance if needed. Now, the cool part about insertions, and now I'm not going to prove this for you, but it'll become very, hopefully apparent the more you play around with AVL trees, is that at most one rebalancing operation is required. You'll see when I get to the example, I'll explain this a little bit better. So let me write down the algorithm. And there's really kind of two pieces. So So I'll write down first per AVL, and then I'll do an example with you, and then I'm going to write down the pseudocode for the rebalancing, because that's easily the most complicated part about this. So let me just write down putAVL first. So putAVL, going to take the root, key, and some data. So the input is going to be root R of an AVL tree. And record K data. So output is just going to be simply, so it's just going to result in me performing, I'm going to insert K data and rebalance as needed. So that's my input, that's my output. This is going to look deceptively simple. It's because the rebalancing does all the work. So I'm going to just apply put R, K, and the data. So I'm just going to assume no duplicates, duplicate keys. So I'm going to assume there's no duplicate keys when I do this. You can make a small trivial modification to this if you want to care about that. So now what I'm going to do is I'm going to let V be the node where K, data was inserted. Okay, so you can do one of the two things. So now remember that put, it returned true or false. What you could do is you could easily modify put to return you the node where it was inserted. Or you could just simply use get. If you want to use get, you can use get, but probably it's much easier to just modify what put is. Okay? So I'm just going to mention, so I can just say modify put or use get. So either use modify put or use get to get V. Then lastly, we'll just call rebalanceAVL, which is going to be the kind of the meat and potatoes of the AVL trees operations. I'm going to apply rebalanceAVL on V. And that's it. That's it. Now, how does the analysis work out? Now, I have not told you what rebalanceAVL is, but let's look at the rest of this. So, put takes how long? Put and this right here, I could do this in big O of H time, right? Now, we'll come back to this in a bit. I want to do an example with you. And then we'll write down what rebalanceAVL does. So what we're going to do is I'm going to draw out a binary search tree. So this is my tree. What I'm going to do is I'm going to insert 40 into this. So I'm going to insert 40. Now in the notes I do go through this step by step, but I want to show you how I'm going to do this. First I'm going to insert 40 into this tree. Now I'm going to insert another record into this tree. So first I'm going to insert 40. Where should 40 go? So where's 40 going? Okay, so I use, in the put operation, I use get to find where it should be. It's right there, right? It's a leaf, so I know I don't have a duplicate. So what do? I put 40 right here. Like this. Now remember, we have an AVL tree, so remember all of these store their heights. So So remember, you would initialize these leaf nodes with height 0. And then what's going to happen, actually, let me just make sure that these are up to date before I make the modification. So before I updated the height yet, remember, I'm going to update this height eventually. This would have been 1, this would have been 2, this would have been 1, and this would have been 3. So I've just created this node. After I've used put, I get this node. And then what I'm going to do is I'm going to recompute the height on this internal node, which is what I alluded to when I talked about how recompute height works. I'm going to assume it's going to get called on the internal node, and it's going to work its way up the tree. So I recompute the height of this node to figure it out. So 0, 0, 1 higher than that is 1. And now what I'm going to do is the following. Now I'm going to change markers so that so it's a bit apparent what's going on. So I'm going to use blue. So when I go up this tree, I'm going to be going up following the parents. So I follow up the parent. I look at this one, okay? I recompute the height because it's an internal node. It's guaranteed to be an internal node because I started at an internal node. I recompute its height, it's 2. 0 and 1 are its children. Does this differ by more than 1? No. So what's happening is I go up to the next parent. I recompute its height. Do I recompute its height or do I do that after? Maybe I should recompute its height last, right? What I should do is check its children. Because remember, once I know the heights of its children, I can recompute the height, correct? Right? But what's happening here? I have 0 for the left and I have 2 for the right. Uh-oh. Uh-oh. This violates the height balance property, so what should happen? What should happen? I should apply a rotation. But what's Z, Y, and X here? What's Z, Y, and X? Okay, that's where the imbalance is occurring. This is Y. Remember, this is the taller of the two children. And what's the taller of these two children? It's just the one with 40, right? So Z, Y, and X. It goes right, then right. That means you're going to use what kind of rotation? An RR rotation. So we're going to apply an RR rotation. An RR rotation. So what do I need to do with the RR rotation? I promote which node gets promoted? Which node gets promoted? This one. Remember, we rotate Y. So now remember, you got to keep in mind what the heights of these things are. Be very careful. So what's going to happen is I'm going to promote Y. Then Z is going to come down, and then it's going to grab this subtree, which happens to just be a leaf, right? So let me just draw that out. Okay, so the heights, remember these are the heights. Did 40's height change at all? No, right? It's just still 1. Did 17's height change? Yes, it did. Yes, it did. So we better update that. So what's the height of 17 now? It's 1. And now this is 2. Now remember, this is the root of the subtree that I've performed the rotation on. So when I finish my rotation, I return back this node so I know how to follow to the next parent. So I go up to the parent now. After I've computed its height, remember I compute the height here, then I compute the height there. Remember the height didn't change here. Then I go up here. Okay, 1 versus 2, they don't differ by more than 1, so we're good. I recompute the height, it's just 3 still. So, and we're done. Yay, yeah, we're done. So that's how you perform an insertion into an AVL tree. Okay, so now what I'm going to do is I'm going to perform another insertion just to illustrate this again. So what I'm going to do is I'm going to insert instead into this tree. What am I going to insert? Let's insert 19 into the tree. Okay, so now I have this tree, and I'm going to insert 19. Where should 19 go? Where should 19 go? Well, 19 is bigger than 12. It's less than 30, but it's bigger than 17, so it better go right here. 19 is right here. So these have height 0. This is, I remember, now I compute the height, which is 1. Then I go up to my parent. Then I check the two children. Is this node height balanced? So is the tree here height balanced? Yes. I compute its height. It's 2. Then, okay, 2 verse 1. Remember, I have to go up to my parent. I check its children. 2 verse 1. It doesn't differ by more than 1. Then I recompute the height of this node, so I get 3. I go up to my parent. Ooh. Okay, 1 versus 3. So what's Z? Z is 12. What's the taller of these two? That's Y. What's the taller of these two? It's 17, so that's X. So what do we need to do? What kind of rotation? A right-left rotation. So what do we need to do? So I'm going to draw this one separately because it's a little bit more complicated. So if I have a right-left rotation, so what's going to happen? So I apply rotate to X, so X gets promoted, Y gets demoted. Let's focus on that first. Okay, so I apply what kind of rotation again? A right-left rotation. So I'm going to first do rotate on X. So 17 gets promoted. That means that 30 is going to get demoted, and it's on its right is 40. Then 19 was originally going to be on its let's take a look at this. So so this goes up, so this gets promoted, that gets demoted. So what's going to happen? So on my left, where does 19 go? Where does 19 go? Remember, where does it go? This one goes up. This goes down. And then I need to trade something, right? So now this is going to get swapped because it's a little too heavy, right? It's going to go over onto that side. So now I have 17. Now does 17 have any children? No, it's just a leaf, right? The heights of these were 0. 19's height didn't change. 40's didn't change. 30's did change. Now its height is 2. Now, before we get a little ahead of ourselves, remember, we aren't done yet. We have to apply rotate again, right? This is still X, right? So I need to apply rotate again. So that means I'm going to promote 17 to become the root of the tree. So all I'm going to do is I'm just going to promote 17 to be the root of the tree. Now, what's going to happen? Well, this is still a part of this tree, so I'm going to just... Now remember, this is going to get traded over to that side, so I'm just going to get rid of that. I'm just going to move all of this up. 30, 19, 40. Crickets are going. Okay, so 17 got promoted. Then what happens? I demote 12. However, remember 17 still technically had a left, it had this leaf node here. So that leaf node went up, and now it's over hanging out with 12. So it's hanging out with 12. Sorry, I'm blocking a lot of this. So if I have 12, then, remember I demoted this, right? So that means the left child still is 11 of 12. So remember the heights of these were 0. That was 1, that's 1. This is 2. This was 0, 0, 1. That was 0. This becomes, what's the height of 12? It's 2. Remember we'd have to update that. Okay, so now I'm done my double rotation because I've updated this. And notice I'm at the root, so I'm done, right? So there we go. There's the double rotation. So I performed the RL rotation, and this is the result here. So sometimes I find it easier to just imagine this happening in my head where you promote this, then you push that down, and then this gets pushed up like this rather than breaking the two pieces. I sometimes find that that's very helpful when I'm trying to do it in my head. Rather than breaking into two pieces, so that I can just kind of just imagine, okay, well 17 was right over here, so it went like this, and then it went up like that, okay? So there's how I do the rebalancing. Now, in the notes I give one more example where I insert 10 into the tree. You can take a look at that in the notes. Now let's write out rebalanceAVL, because I said that that was easily the trickiest part of doing this stuff. So I'm going to give you the algorithm. So here's the algorithm. This is rebalanceAVL. And it's just going to take in some node V. So it's going to take in node V, where imbalance may have occurred in the AVL tree. Okay, the output is update AVL tree to now be balanced. Anyways, here's the algorithm. So I'm going to have if V is not a leaf, if V is not a leaf, then we're going to apply recompute height. Recompute height. We're going to apply that to V. That's why I said you can assume that the internal node's height's going to get updated because the algorithm is going to do it there. That's when that happens. Then I'm going to have a while loop. I'm going to say while V is not the root. I have to be very careful here. This is not just, the root might actually change in this rotation process. So be very, I'm warning you right now that you have to be careful. So while V is not the root, you're going to assign V to be the parent of V. Remember, we go up to the parent. And now we're going to check if that node is height balanced. So by checking its children. If the subtree rooted at V is not AVL, then so this is when the heights of the children differ by more than 1. So what I'm going to do is I'm going to let y be the tallest child of v, and let x be the tallest child of y. What's z in this step? Z is in fact v. So in our pictures, wherever I have z, that's v here. Now I'm just going to remark that if ever there is a tie, wherever there is a tie, when picking x, go with the one on the same side. I'll put that in quotation marks. So what do I mean by this? Now, this is just a performance thing. If I run into a case where the tallest among two is tied, just pick the one that's on the same side. So for example, if I went right, then I want to make sure I pick, if there's a tie, pick the right one as opposed to the left one. This is to ensure that we use a single rotation as opposed to a double rotation. Generally, that will be a better thing from a practical standpoint to do. Theoretically, it doesn't make a big difference. So rebalance subtree rooted at V. So we're going to rebalance subtree rooted at V by performing appropriate rotation. So you're going to apply the appropriate rotation here. So you're going to apply an LL, RR, LR, or an RL rotation. And I'm just going to make sure to update the heights. So I just want to make sure you update the heights in that process. And then all I'm going to do is I'm just going to let V be the root of the resulting subtree. So remember, like I said, whenever I'm doing these rotate operations, I want to just make sure I pick up from where the rotation happened, okay? And then what's going to happen? What did I do after I knew that the thing was balanced up to that point from bottom up standpoint? I recompute the height, right? So I'm running out of space here. I'm just going to write the last bit over there. I swear it's like a little tiny bit. So imagine I'm going up here. Outside of the if statement, outside of that if statement is going to be recompute height. So this is occurring outside the if statement, but it's still in the while loop. So I'm going to recompute the height of V. And that's it. Like I said, barely. I just had enough room there almost. So I'm just going to recompute the height of V, and then I do this over and over again until V is not the root. If it becomes the root, what does that mean? So V is the root itself. So when remember, every time I assign this to be the parent of V, right? So when I finish this process, if I reach the root after I've computed the heights and everything, because remember, every single time I do this, I go up to my parent and then I check the height balance property. It's not the other way around. So I check the node before I check that condition there. So I would have moved up and checked the height balance property here, and then it becomes the root. So I know it is the root, so that's how I know it's going to finish. So hopefully this makes sense. So I'm checking this condition. This is a valid termination condition because I would have checked V, which already could have been the root. Okay? So we'll work our way up the tree, apply the rotation if the height balance property gets invalidated. We have to just determine what V, Y, and X are. Okay? So let's do the analysis. And then we'll do the analysis for putAVL. We might have enough time to talk briefly about remove, and then next day we'll finish things up with the AVL trees. Okay, so if it's not a leaf, so this clearly takes constant time, right? This is just some, what is that? That is some constant, I'll just call it C1. So this is C1 here. Okay, how about this? What's happening inside of all of the while loop's body? So all of this, including here. How long does all of this take? Well, that takes constant time. Checking this condition takes constant time. Determining that takes constant time. Rebalancing a subtree rooted with the rotation. Remember, we established the rotation takes constant time. This whole thing just takes constant time. So I'm going to call that C2. This while loop. The while loop. How long does that, how many operations is that? It's going to be C2 times what? Times what? Well, I work from the bottom of the tree, wherever I did the insertion, up. How big can that path be? It could be the overall height of the tree, right? Which is H. So, how long does this rebalance AVL take? How long does rebalance AVL take? So rebalance AVL takes big O H time, since H is big O of log n, it takes, and when I say it, I mean rebalance AVL, it takes big O of log n time. See, isn't that nice? So that knocks out this analysis, so we know that rebalance AVL takes big O of log n time. But we also know it takes big O of H. So we know this takes big O of H, but H is big O of log n. So putAVL takes big O of log n time, and we're done. So we did the analyses for 2 algorithms in like a minute and a half. So is that cool? So that's putAVL and rebalanceAVL. So one thing I want to mention is why this one rebalancing operation is required. So why is it not many of them? It's only just one. It's because when you do the insertion, where does the insertion occur? It happens at a leaf node, right? It's not just anywhere, it's not an arbitrary place in the tree where it could affect multiple parts of the tree. It only happens at one spot, at a leaf. So when I do the insertion, when's that rotation going to be required? At the smallest possible subtree where an imbalance occurs. But remember, the AVL tree was already balanced before I got to it, right? So it means that if I put that in and it causes an imbalance, it would have, all the rest of the tree was already balanced in the first place. So all I'll be doing is rebalancing that subtree where the imbalance occurred. That's why we only need one. I'm not going to prove that for you, but that's generally the intuition of why. That is not true when I do a removal, though. So let me just quickly jot down a little bit about removal, and then we're going to stop for today. So I'm just going to say apply, remove. So what we're going to do naturally is I'm going to apply remove of the BST. Then from the parent, of the removed node. I'll talk more about what I mean by the parent of the removed node next day. Rebalance the tree. Now, I must stress that several rebalancing operations may be required. So, several rebalancing operations may be needed. So, here's the algorithm. Just like putAVL, removeAVL is going to be very short and simple. removeAVL, it's going to take the root and some key. So R is the root of an AVL tree. Then I have some key K, the one I want to remove. So I'm going to output. What's going to happen? I'm going to remove K from the tree and rebalance if needed. So I'm going to rebalance if needed. So you're going to naturally think, okay, well, how am I going to do this? All I'm going to do is I'm going to apply remove, given the root and the key, just like I had before. Now I'm going to say, let V be the node where removed node used to be. Now, if you're wondering what I mean by this, this is C prime in the pseudocode of remove. So this is C prime in remove. So if you remember back to the notes on remove, think of C prime. Now, you might ask, oh, well, that isn't really the parent of the one I removed, right? I'm getting to that. All I'm going to do now is just apply rebalanceAVL. And I'll apply it to V. So remember, rebalanceAVL, I don't have it here. It's on the other side. It's on the flip side. What it does is it will go immediately up to the parent after recomputing the height, right? So that's why I need the case to check if it isn't the leaf, right? What is the parent of the removed node? Well, it's the parent of C prime. So that being said, the algorithm will automatically do this. So if you're wondering why this doesn't match up with that, it's because removeAVL will immediately go to the parent of C prime. Okay? What's the worst case running time of this? Well, we already established that takes big O of H, this takes big O of H, so this whole thing's big O of H. And as I said before, H is big O of log n. So removeAVL. My writing, man. Right, so removeAVL takes big O of log n time. And we're done. So that's how you're going to perform the removal. So next day we'll do an example of performing removals. And then I'll talk a little bit last bit about AVL trees. Then we'll hopefully maybe have time to talk a bit about something else. I'm getting really excited about the next topic. Anyways, that being said, thank you very much and have yourself a beautiful day.